Welcome, my name is Pawel Rajba and I will talk about data hiding using code obfuscation. This is the joint work with Wojciech Mazurczyk from Warsaw University of Technology. In digital era, information can be hidden practically everywhere. The most popular are images, videos, but also we can hide messages in voice network traffic and others. JavaScript obfuscation, on the other hand, is a recognized technique for the intellectual property protection. The main contribution of the paper is to connect those together, to leverage on JavaScript obfuscation to hide secret messages. The main purpose of obfuscation is to make the code unreadable. That's the main goal here. However, usually when we talk about obfuscation, we want to evaluate three main properties: the potency, the main goal here, resilience, resistance for the automated obfuscation, and the cost, the increase of execution time space required after obfuscation, since obfuscation usually increase the size of the code is much bigger to be executed. Some common examples on the code modification during the obfuscation process are as follows. It's a string array. It means that we collect all the literals and put as an array at the beginning of the file. Identifiers replacement, dead code injection, control flow flattening, content encryption, and others. In our method, we primarily leverage string array and dead code injection properties. Obfuscation can be visualized, and here you have a small example how it works. On the left side there is a small snippet of code, and on the right side is the obfuscated version. Obfuscated version, after enabling all the potential available features, obviously we can enable smaller number of features or bigger number of features. Here we can see the full power of obfuscation. Looking at this file, we can observe this red fragment at the beginning here, the place when there is the first array created, when there is a number of items in it. This array appears after enabling string array option, and it consists all the literals that we mentioned, but also it includes randomly generated literals to support dead code injection. We, as a primarily way in our method, we replace this randomly generated strings from the table by the secret message. That's the main way how our method is working. Before we go into details, let's review the scenario and thread model. Generally speaking, we have the client-server model. Web browser is requesting web content from the server, then web service is generating this content, including JavaScript files, which might be obfuscated with the secret message in it. Once the web server prepares the message, the content, it sends back to the browser, and then browser has the possibility to extract the secret message. Moreover, we may have some more complex scenario with reverse proxy and proxy involved. Then the obfuscation and potential embedding might happen on reverse proxy, and on the other hand, on proxy we might have the extraction process. The embedding process consists of two main stages: message generation stage and then embedding the message into the file. Let's review first the first stage, message generation, by examining a small example. Let our secret message be let the cat out of the bag. After we encrypt the content with AES, we obtain a ciphertext that we can see now on the screen. This ciphertext is encoded with the standard ASCII characters. In the first stage, we want to transfer this encoding into the single integer encoding. I mean, change the encoding base to the decimal base. Here the thing is that we consider this whole ciphertext as a single number and put it as a single integer. Then in the next step, we take the single integer and change its base into the 52 base. to be able to encode this message with upper and lowercase letters. The reason why we do that is because in the original obfuscation process, the randomly generated strings are generated using upper and lowercase letters. So to make indistinguishable from the original obfuscation process after comparing to the one that we influence by including the secret message, we want to use exactly the same character set. Finally, we split the message into 5-letter chunks, and that array is ready to be included in the JavaScript file. When it comes to including the table of secret strings, secret messages into the JavaScript file, it's quite straightforward process. However, we need to investigate two things. Either we have a challenge in identifying which entries are from the dead code once it is generated, or during the obfuscation process, we might have a problem with finding the correct order in which they appear in the final generated file. To somehow cover both the problems at once, we introduce placeholder concept. So instead of embedding secret message during the obfuscation process, we embed actually placeholder during the obfuscation process, and in the after processing phase, we replace all the placeholder with the actual secret messages, this array that we've seen before with these 5-letter strings. This is how it looks like. We have as an input this array of consisting the secret message, and then also as an input we have a list of this array in obfuscated file with placeholders available. Then of course we replace placeholders by the items from the secret message table. Extracting process is quite straightforward as well because it's about reversing the original process. However, we need to resolve one problem. Once we receive the message, we need to somehow identify which items are constituting the secret message. And we solve that with a very simple way. After receiving the table A in the obfuscated file, we run the obfuscation process again on the client, but with no dead code injection option enabled. And by that we obtain array A'. Then we just remove items A' from the array A, and by that what is left is our secret. In our experimental environment, we use JavaScript obfuscator as a base obfuscator, which is modified to be able to include this placeholder instead of randomly generated strings during the dead code generation. Encoding, decoding functionalities are implemented in C#, and also other tooling required is also implemented in C#. Test files are taken from CDN.js library. And finally, we have for our experiment for further investigation 6,000 and over 6,700 files. In our analysis, we evaluated 3 common properties: robustness, stealthiness, and data hiding capacity. Robustness is about to ensure we can either detect errors and/or correct errors. Errors obviously can be accidental or intentional. And in our proposal, we cover only detection by introducing MD5 hash. Error connection is not covered in this paper, but of course we plan that in our future work, being aware that introducing robustness, we need to be careful to reduce the impact on data hiding capacity and stealthiness. Stealthiness is a property to ensure that secret communication remains undetected, and in our proposal, it's not possible to distinguish the normal traffic from the traffic with the hidden message. So somehow our method is completely stealthy. This is based on the characteristics of the AES ciphertext, because by some research, AES artifact is indistinguishable from the random string. So we believe that by that stealthiness is very much secured. Data hiding capacity is about to measure how much secret data can be transferred during the communication, and we use our CDN.js files as a reference point. Reference point in a sense that usually we use obfuscation for our proprietary code to be secured. Obviously, we can increase the overall security of our system by obfuscating everything, but still, most likely, we are interested in our proprietary code to be obfuscated and by that secured. In our method, we use dead code injection, and this dead code injection can be configured. The level of that injection is configured by the parameter from 0 to 1. The default value is 0.4, and we evaluated 5 values from 0.2 to 1.0. First, we checked how much the code size increased after enabling the option, and then here you can see result in the table. Then that code size increased from 28% for the smaller level of injection to 132 when we enable the highest level of injection level. Then we investigated how many strings are available in files that are obfuscated. So we analyze that from all the injection levels, and then here on the diagram you can see the ranges. I mean the number of strings in the array, and the number of files, obfuscated files, that are supporting this range of strings in array. And as an observation, we can see that the smaller injection level is, the more smaller size, small sizes of arrays are being supported. The more injection level, then there is a less file supporting smaller ranges, but then we have bigger ranges supported by more files. As some kind of summary or aggregation, here we can see what is the average number of strings available in files. So we can see those values, and then we can also observe that for the default value, it's almost 190 strings available on average in file. Assuming that each character carries 5.7 bits, based on what you can see here, using the formula as expressed, we can calculate the average number of bytes available in each file. And it's based on the calculation, it's over 600 for the default option, default dead code injection level, what seems to be quite significant number. Now let's investigate efficiency coefficient. Let K be the size of the obfuscated file, and L be the file capacity for secret message, what means how many bytes can be hidden in this specific file. Efficiency coefficient is E equals K by L, and that is the number of bytes required to send 1 kilobyte of the secret message. Obviously, the smaller E, the better. And then having L values and K values for our CDN.js files, we can calculate efficiency coefficient, which is almost 200 bytes for the default option. Another perspective, when we consider Alexa top websites, then we can then we have 7.5 gigabytes JavaScript transfer per day. If we assume that all of this content can be used to smuggle secrets, then we obtain these numbers of megabytes that daily can be smuggled. It's quite significant values here. Even if we assume 1% of this, what is the actual number of content today, still it is very significant content that can be smuggled. Countermeasures, as we observed and discovered already, its stealthiness is completely secure, so we are not able to detect this the content, but we can easily destroy it by just replacing one of the items. In our future research, we want to look into selecting the right item from the array in an efficient way. Conclusions and outlook: we presented a new approach for data hiding in web content. Experimental results prove that the method is feasible and can be practically used. And then when it comes to the future work, we introduce error correction techniques. We want to look into other techniques which doesn't require dead code injection, for instance, investigate other obfuscators from the market, and investigate safe countermeasure techniques. Thank you so much for listening, and I'm open to answer your questions.